We will start an important and a very useful theorem in modular arithmetic. So, if A is congruent to B mod M and C is congruent to D mod M, notice that here the M is the same, so they are working on the same clock. Then, A plus C is congruent to B plus D mod M, and we will have a simple proof. So you see here, our aim is to prove that A plus C is congruent to B plus D mod M. So what we have to do is we need to show that this A plus C, when it minus B plus D, is indeed a multiple of M. So what information do we have? We know that A minus B is a multiple of M. Let's say A minus B is M times K. And then C minus D is also a multiple of M. So we will write C minus D is equal to M times L. So from here, I know that A plus C minus B plus D, this thing, can be written as A minus B, which is this one, plus C minus D, which is this one. So right now what we have done is we remove the bracket and we change the position of the terms. Then I know that A minus B is actually M times K. And I know that C minus D is M times L. So A minus B will be replaced by M times K, and C minus D will be replaced by M times L. So these two things add together, I will have M times K plus M times L, which is M times K plus L. These things right now becomes a multiple of M. That's why A plus C is congruent to B plus D mod M. For example, 12 is congruent to 2 mod 5. 9 is congruent to 4 mod 5. We're working on the same 5-hour clock. Then 21 is congruent to 6 mod 5, which is also equal to 1 mod 5, because 6 in a 5-hour clock means 1. So right now we will test, so 21 minus 1 is 20. 20 is actually 4 times 5. So 21 is congruent to 1 mod 5. We are right. So here is another theorem. A is congruent to B mod M and C is congruent to D mod M. Then I said A times C is congruent to B times D mod M. So what we have to show is AC minus BD is a multiple of M. I can use the information from the previous theorem. So A is equal to B plus MK and C is equal to D plus ML. And then I can substitute A and C into here. And then after some algebraic manipulations, we know that AC is congruent to BD mod M. So examples. 12 is congruent to 2 mod 5, 9 is congruent to 4 mod 5. When I multiply the numbers, then I know that 108 is congruent to 8 mod 5. 8 actually means 3 in a 5-hour clock. So now we can test it. 108 minus 3 is 105. 105 is 21 times 5. So 108 is congruent to 8 mod 5. But this theorem would be very useful. Say if someone asks you when 11 multiplied by 51 and the whole thing divided by 6, what is the remainder? So instead of doing 11 multiplied by 51, what we do is we find the remainder when 11 is divided by 6. And we also find the remainder when 51 is divided by 6. Then we only need to multiply these two remainders, and then we can have a smaller number so as to find the remainder when this product is divided by 6. So we can see that instead of finding the product of a large number, we can actually find the remainder of the smaller numbers, and we only need to multiply them. Let's pause here and then I will see you in the next video.